here to talk about my favorite topic, RDMA, and how can you enable remote persistent memory using RDMA. So my agenda here, I'm going to speak about the workloads, like the workloads that we are focused at from the standardization point of view. Then I'm going to speak about I'm going to speak about our memory placement extensions that we are proposing in InfiniBand. I'm going to have a little talk about memory management, and then I'll summarize. So what are the workloads? So the first workload, which was presented here by the NVM PM work group in the document called Remote Persistent Memory for High Availability. We want to replicate memory files or blocks, and we want to replicate it to a remote persistent memory. It includes several things that have to be done. One, you will probably have a scatter-gather list. So your memory will probably be scattered in memory your data will probably be scattered in memory somewhere, and you would need to collect this data and push it to the peer memory. You would probably need to do it. Yeah. You would probably need to do it asynchronously, because you don't want to wait for the user to do an optimized flush or a sync in order to start flushing the data out from your memory, because it will take time, and you want to reduce that. You want to amortize the time that it takes to push the data to remote memory using asynchronous flushing, and you want to verify persistency. So those are the challenges. You may also want to do some integrity checks, like for example, verify that the data hasn't been corrupted through the network or while getting into the memory. And you may want to encrypt it as well, so the data will be encrypted at rest, so it won't be stolen by. So it will be protected at rest. And if this device will be stolen, you will be protected. Another problem that we looked at is the two-phase commit problem. We've seen this as a typical workload in file systems and databases, where you wanna update data, and you wanna commit this data into memory, probably with updating a pointer or a flag that explicitly say that this data is valid. So you probably have two chased operation where you would write data to remote persistent memory, and then you would like to verify that this data is persistent, and only then you would like to write a flag or write a pointer to this data or replace a pointer to this data. So the flag or the pointer must be committed to the media only after the data is committed and verified that has been committed successfully. So we've addressed these challenges in our InfiniBand RDMA memory placement extensions. So just a general overview about RDMA. How the RDMA provides the capability to access remote memory either with reads or writes, a remote buffer using one-sided operations, which basically means that if I want to read from a buffer of one application, from a buffer of remote application to my buffer, I post a request to an adapter. This adapter will transmit a packet to the network, and this packet will either update remote memory or get data from remote memory without the notification on the other side. So it's interaction with memory. With remote memory as it was local, without any awareness of the other side of the application on the other side of the network. The principles, the RDMA principles, is built on a few simple primitives. One is called the queue pair. Its meaning is a connection. So basically, every node that wants to communicate with another node, it will have a queue pair. You connect in order to establish this connection. You can register a memory region, meaning I, as an application, I can take a part of my memory, and I can tell the adapter this memory can be exposed to remote, right? And while I'm telling the adapter, I can add many attributes to this memory, which will be discussed later. I can send and receive for doing messaging, similar to any other networking protocol. But I can also RDMA read and RDMA write towards a remote memory that was registered. And the reliability defined as delivery once and in order. Okay, so if I write to a location, I write it only once. If I write data to a location, I write it only once. I write it in the order of writes that I have posted from the requester side, and I write it in order. So what is the reliability scope of current RDMA? Current RDMA, the reliability scope is a transport level reliability, meaning if I want to write to a buffer, to a remote buffer, I will post this operation to my NIC or to my HCA, depends on the protocol, and this NIC will start transmitting RDMA writes packets. I will get acknowledgements on these write packets once those packets have arrived to the remote side. So it doesn't mean that it has arrived to the host. It doesn't mean that it has arrived to the memory. It just guarantees that the packet has been delivered. So I won't need to retransmit this packet because it has been delivered to the other side. It doesn't mean, for example, that this data is visible to other connections. Okay? It just means that these packets have traversed the network, and I got an acknowledgement that I won't need to retransmit them at all. And if you want to implement further guarantees, you need to implement it by an upper layer protocol. Now, upper layer protocol it means that it's out of the scope of this protocol, and it means that it may induce overhead to implement it in an upper layer protocol. Like, for example, you would need some processor that may need to run application in order to process this upper layer protocol. So we are now introducing in InfiniBand a new concept called memory reliability. What you've seen is that our transport was mostly around enabling network reliability, and now we are looking at memory reliability. So one new operation that we are proposing to add to InfiniBand is an operation called RDMA flush. The RDMA flush, our target with RDMA flush is to provide the ability to get memory placement guarantees on transactions that were delivered on this connection. So we want to make a new, we want to enable this new operation, but remain the other RDMA memory operations unchanged. So how do we plan to do that? And let's start with the requirements. What are the requirements of such operation? First requirement is that this operation, if I want to verify that my data is in memory, it may take time. Because it may take time and it may depend on the memory latency, I don't want to hold the networking, to hold the processing of networking while processing this operation. It would be like halting the highway to verify that everyone got home, right? So we don't want to do it. We want to keep this operation. We want to receive this operation and process it on the side. And for that, we need to be able to delay it. So because we want to delay it, we make it a non-posted operations, means it could be delayed. We want it to apply on certain regions because we want it to be selective. We don't want to flush all of the memory subsystem every time we get this packet. We want it to be pipelined. We don't want to fence the whole network because of one operation. We don't want the application on the requester side to wait because it has posted this operation, because it may want to do many such operations, pipelined. and we want to amortize. We don't want to pay for every write that we write. We don't want to pay this penalty of flushing. We may, for example, if a file system doing a sync, we may have several pages to flush, and we want those several pages to be flushed, the flush of those several pages to be amortized. So we want to have the ability for this flush to apply on many, many operations and not on a single one. The system level implications may be caching efficiency or persistent memory bandwidth. And we also don't want to focus only on persistency. We want to enable also global visibility. Meaning, if I do a flush on something I wrote, I want the data to be visible also to other QPs, not only placed in persistency. So we want several types of this operation. So we're presenting a new transport operation. It's going to be able to be delayed, non-posted, and it will have an explicit response. It will be associated with this memory region that was registered, and it will have several placement types and selectivity levels, which will enable all of these requirements that I mentioned before. Now we come to the problem of efficient two-phase commit. Because of these ordering rules, if you want to implement a write of like a large amount of data and then like a flag that indicates that this data is valid, you will need to do several writes, then to do a flush to guarantee that they are persistent. And only after you got the response, you can write the flag. It means that for example, in this example, you would need to wait a round trip until you write this flag. And this is expensive in latency. It's not only expensive in latency, it's also may consume either the CPU, because someone needs to wait, right? So it's either the CPU will wait or the transport will wait, and then nothing will be transmitted. So you have a trade-off here that is costly, and you have the round trip that is costly as well. So another proposal that we have for the transport in InfiniBand is a new operation called atomic write. This atomic write will be a new type of write in InfiniBand, where this new type of write has fixed size. It's like it's 8 bytes. It's for update of flag or update of a pointer. And the thing about this new operation is that it would be delayed as the flushes before would be delayed. Meaning, if I post this atomic write right after flush, and the flush was delayed because it takes a long time, then this atomic write would be queued after the flush. But it won't halt the other large mass data transfers that may wait and don't want to wait behind a flush or behind an atomic write. And in this way, you can reduce the round trip penalty. You cannot have the round trip penalty. You will just have the flush penalty, which is the minimum you must have in order to get your consistency requirements, without any cost of this trade-off. Another thing I wanted to discuss here is a little bit about memory management. So we spoke a little bit about memory region. We said that if I want to let someone access my memory, I need to register it, and I register it in a memory region. So what is memory region? In memory region, I give permissions. I give permissions for read, for write, for flashing, etc. I provide protection domain, which is associating this memory region with a set of connections that can access this memory region. I provide memory layout. Like, for example, I can choose a scatter-gather list in my memory and say, this is the memory region I have. It doesn't have to be contiguous. It just it creates a virtual addressing for a scatter-gather. And I provide today an integrity checking. I can do, for example, I can say that this memory region is protected by tit and diff. And the adapter needs to add tit and diff or strip tit and diff when there is access to this memory region. So that's nice. And there is a control plane around these memory regions. Like, for example, in the NVMPM, they have mentioned that you register this memory region once you do an mmap. and that you invalidate this memory region once you do unmap. So mainly, this control plane is mainly being used while configuring the system before the data pass has occurred. Now, what we support today in InfiniBand is the ability to add and strip integrity checking based on this memory region. So think about it this way. I register a memory region to be accessible by remote. Now I can associate this memory region with a feature. One of the features is I'm adding CRC and uptag and reftag, which is tit and diff, while the data is coming in towards the memory. And I'm stripping it while the data is coming out from memory. And therefore, I'm validating the integrity of this access towards persistent memory on the flight because of these memory region attributes. So that's nice, and that's basically the way to verify integrity. And another thing we are looking at is how to do encryption. And again, for data at rest, you must people may want their data to be encrypted in persistent memory, and especially when it's remote and it's a server you're not controlling at, you're not going to fail the application if something will happen to this server. So what we propose here is working in a similar way. We would like the registration of this memory region to include a key for encrypting or decrypting the data. Now, there are many memory regions, and they can be exposed to many different applications and many different services. So each and every memory region could be associated with a different key, and there would need to be a key management in order to make it work. But essentially, what you'll get end-to-end is that all of your data will get encrypted or decrypted, depends on if it's a read or a write, towards this persistent memory. Another alternative is to do it end-to-end by registering this memory region on the initiator side. So let me summarize here. InfiniBand right now is building the foundation for remote access to persistent memory. We discussed their memory reliability, security, data integrity. We have working progress annex that is going to be exposed through the InfiniBand community. And we are more than willing for other partners to come to InfiniBand and contribute. To make a complete story on the system level, these challenges should be addressed also in other standardization, like, for example, interfaces of memory. And what is mainly missing is PCI. So if there are PCI folks here, I guess we would appreciate to educate about the studies that we've did about how to build a protocol, and there is a need to do those things in PCI as well in order for the whole system to support it. That's all.
While we bring up Dave and the esteemed panel coming up, maybe time for one quick question for Idan. Anybody? Any takers? Go ahead.
This last point was not very clear. What's the PCI intersection of this capability? I mean, this is RDMA, right? So what's the PCI?
When you build a system today, you want to build a system built of an adapter with a bus towards memory. For example, InfiniBand adapter or Ethernet adapter, that it has to access memory either through PCI or through other bus technologies, right? So we have the component that we have standardized. We are now standardizing the whole network path, but we are missing how to interface the memory itself from such adapter. So bus technologies like CCIX, like PCI, is what's missing right now for us to build the complete story.
All right, let's give the speaker a hand.